Yes, sir.
So wherever you are generating clock bar, whether it is in the PLL and then you're routing, making a full clock tree for clock bar also, or you're saying taking clock inside your latch and inverting it there itself and using it, whatever you choose, do you
Okay.
realize that there will be some delay?
Yes, sir. Some delay. Okay.
है ना?
Okay. Thank you. Yes,
Yeah.
sir.
Okay. So just like we drew the latches, we can also make flip-flops. A flip-flop is essentially a pair of back-to-back latches. So if I do not want to go to a very stable feedback-driven circuit, I could have a latch which has floating gates like X. Or I could have a latch like this one, where my outputs do not even touch or influence the inputs in whichever possible way. So which flip-flop do you think will be most commonly used?
It's the bottom.
The lower one, because it's much more robust. Even though it is much bigger in size, but it is more robust. So we use something like this. Raghav?
So in this both this the additional inverter that I'm using, that is just for the functionality, right?
That is just so that I do not end up influencing the internal node, the latch, from the output.
Okay. So, but like no, in the second design, after that, after I've isolated the Q bar, I'm still adding an additional inverter that I don't need, right?
I need Q and Q bar both. In a flip-flop,
Okay.
you will see both outputs are usually there.
Okay.
So those
Okay.
inverters are put inside the flop itself.
Okay. So the back driving issue to minimize that. Okay.
Yes. Okay. So now you remember we talked about clock gating, where we said that to reduce dynamic power, we will gate some parts of the circuit so that there is no clock toggling there.
Yes, sir.
So that we save power of toggling of signals. So clock gating is enabled in flip-flops and latches by using the use of this signal called enable. When enable equal to 0, any transition on clock is ignored. And you can implement this system in two of the ways, either by using a multiplexer or using a AND or an AND gate. Are you able to see this? Any questions here? Are you able to see that if clock equal to 0, the output will become independent of clock? If enable equal to 0, output becomes independent of clock. Are you able to see that?
Yes.
Yes, sir.
है ना? So, any questions on this? Functionality is evident, fairly evident from the slide itself. Okay.
In this multiplexer one, the multiplexer thing, sir, there don't we even give an extra constraint of like enable should come first, then D would settle, and then the clock comes. I mean, the enable and D will also have some because the
Enable is not a clock. Enable is a signal. So those regular signals के बीच में you don't put constraints. Clock and enable, yes, there is a constraint. Clock and data, there will be a constraint, but not between data and enable.
that is considered to be combinational only.
Yeah. है ना?
Yes.
Okay.
Can you elaborate? So can you elaborate on this point? Clock gate increase in setup skew. I mean, how is the skew getting affected?
How is the skew getting mapped? We actually just keep this with yourself. When we will talk about the timing, you will see what skew is.
Okay, sir.
Abhi to I have not even introduced the term skew to you, na?
Yes, sir.
अभी बस उसको park कर लो. Just park it somewhere. You will see how this Q will get impacted. It will be evident to you.
Okay. And so in the multiplexer based design, when my enable is say 0, I mean, how is the clock? I'm like isolating from the clock when with the enable signal, that I was not able to clear.
So the latch is not changing or not going to D. Na? D will not reflect on Q until enable is 0. Because the input of the latch remains constant, which is equal to the output.
If
When
my
enable
enable
equal
is
to 0, when enable equal to 0, what path gets activated in the multiplexer design?
so the D1.
Enable
Okay.
equal to 0.
Okay, okay, yes, yes, sir.
है ना?
Yes,
0.
yes.
So enable equal to 0 means this path is activated. So any change in D will not come into picture.
Okay, 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 sir.
Same here. You see?
Yes, sir, yes, sir.
ठीक है?
Yes.
Now, Tarun?
No, sir, actually Raghav asked that out.
I'm sorry? हो गया doubt.
Oh yeah, that was asked.
Okay, great. So now, in addition to enable signals, you will see that flip-flops also sometimes have what is called as a reset signal. What does reset mean? Reset means that the output will be pushed to 0. Output will be pushed to low when reset is asserted. And it could be synchronous or asynchronous. The first implementation is synchronous one, where output will be pushed to 0 at the next rising edge of the clock or whenever the clock is high again. This one, on the other hand, is an asynchronous reset, where by using reset on additional gates inside the latches, I have ensured that as soon as reset comes, my output will be 0. Are you able to see this? Why do you think this reset pin is even necessary?
Sir, maybe while putting my circuit into sleep or uh, getting some part of circuit, I want to bring it to a present state that is predetermined. That kind of functionality.
I suppose power up is happening. A power up has just happened, and now you want to say that, okay, I want to start with a clean slate. During power up, some latches will be 0, some latches will be 1. I have no control over anything. You know, some latches could be 0, some. So I just assert reset. All the flops, everything is 0 now. Now it is the deterministic state that I'm starting from.
So what is power up? Okay, like on off.
Yeah.
Okay, okay, okay.
Okay. Now, when you do this power up, do you really want all flops to be 0? Or there could be some flops because of the state machine requirements, you may want them to be 1 also. It can happen.
Yes, sir.
So that is what takes us to the next kind of a flip-flop, which is set reset flip-flop. Where if you want to set, then something would happen. If you want to reset, something else would happen. So in this case, what you do, you are able to create the state machine that you desire. You obviously notice there are many more transistors in this flop now. And all the inverters are converted into 2 input gates at least, if not more. है ना? ये तो tri-stated gates हैं. This has many more transistors now. But if you need this functionality in a few flops, you will use the set reset flops at those places. At other places where they are not a part of the FSM of the system or anything like that, you may still use the regular reset flops or the regular flops also without even reset. But some flops in the FSM, you may want to use set reset flops so that you can power up in a desired state machine. And then therefore give faster output to the user or whatever, faster, better experience to the user. So you'll lose some area, but you will have a deterministic power up, by using the set reset flop. Okay, any questions?
So sir, like with this set and reset, I'm trying to control the internal states of the flip-flop, like
And
irrespective.
therefore the output.
Yes, sir. Like it is apart from that normal computation. That exactly. I mean,
Yeah, I'm not even waiting for clock to arrive. I'm saying, let me change the output even before clock arrives.
so but the clock only when it is asynchronous, then only I will be able to control. Otherwise, the synchronous clock has to arrive, right?
Yeah. In this case, set reset is usually asynchronous.
Okay. Set reset both are used with asynchronous only.
Usually.
Okay.
When it is only reset, you can think of synchronous and asynchronous, but set reset flop, people understand it is for the state machine. So the clock may not even be coming at that time
Okay.
because we're talking about power up. The clock may
Yes.
not be active yet. Even then,
Yes.
I may want to have a state machine of my choice.
Yes, sir. Yeah.
Okay. Anything else?
So in the state machine, like why is the need of setting this? मतलब actually में अंदर हो क्या रहा है कि हमको set की जरूरत पड़ रही है?
Okay. How do I put it? There could be a state machine. For example, let us say there is a state machine that controls the configuration inputs of the memory.
Okay.
Now for memory, some inputs are expected to be held at 1 and some other inputs are expected to be powered up at 0.
Okay.
So you need some signals to be powered up at 1 and others at 0.
Yes, sir. Yes, sir. So okay. Okay.
That is why. So now you may think that I may use an inverter, but if the power up has not completely happened, if the power up has not completely happened, then asynchronous set reset will still work. Will still
Yes, sir.
power up the system in the right way, even before first clock arrives and things like that.
Yes, sir.
So now we in the few slides back, we saw that there is this possibility of an overlap between CLK and CLK bar, which can lead to backgate driving and all that stuff. You remember? Then to avoid that, what did we do? We added inverters, extra inverters on the outputs and everything. So by using this true single phase clock flip-flops, I can avoid that altogether. This is called tspc, true single phase clock flops. Here, what has happened is, here you will notice that I'm able to hold the data or make it as a latch by using only one phase of clock. The risk is that this internal node, intermediate node, is dynamic in nature now. So tspc flops are much faster, are smaller, have lesser risk of CK bar overlaps because there is only CK now. But there is a risk of this intermediate node struggling because of noise issues. Okay.
Sir, this looks like a dynamic gate for clock
Yeah.
input, sir.
Yeah, that is why I said none. This is a risk. The node is floating there. So now if you want to include logic in tspc, you can also include logic into tspc latches. But again, always remember, this is a risk. There will be floating nodes somewhere or the other. If both in and in1 and in2 are 1, if both in1 and in2 are 1, then what happens? And let us say ck is also is equal to 0. Then what happens? This node is floating. Are you able to see this? So the output will be tentative. We do not know. It's a risky kind of a design. So see, dynamic circuits without level restorers, without all those checks in place, can be very risky. tspc and therefore will not be used in places where noise immunity is considered to be a very high criteria. Wherever speed is very highly required or something like that, you could still use tspc.
Sir,
Yes.
so, sir, can you please elaborate exactly what exactly are we solving the problem with this tspc? I was not able to get.
So there was you remember there was this tri-state, and we said there is a possibility of Q back driving D when CK and CK bar overlap.
Yes, sir.
है ना? So, and to avoid this, then we added inverters here and we did so many things.
Yes, sir.
Now we say that, is there a way to avoid extra gates, save area? And that is what tspc is solving. Here only CK is being used.
Okay, so I'm doing this to avoid the back driving.
Yes.
Sorry. Okay.
Okay. However, notice that this means that this node is now floating. It comes with a risk. So use it only very, very carefully in a very, very controlled environment, not anywhere else. Okay. Similarly, we have a tspc flip-flop also.
So,
Yes.
so by default, what design do we use?
By default, what design do we use? The static, the one that I showed with so many extra transistors.
Okay. Okay.
The one now without enable is the one that is usually used. Enable one is also required at some places, and then you also require set and set reset flops at some places. But majority of the times, the regular flop will be used without enable and without set reset.
Okay. And so they both need clock and clock bar signals, but by default, whenever we see some synthesized netlist, we only see one clock in any flip flop or
Because the
latch.
clock bar is generated inside the flop.
So using inverter only.
Yes.
Okay.
Okay.
Okay, sir.
Yeah. Gagandeep?
Sir, in the circuits for the tspc, sir, I'm seeing that consistently the clock transistor is nearer to the output node. Why is that?
Output node. दोबारा से बोलो, clock transistor is nearer to the output node.
Yes.
But only so that unnecessary toggling on D, for example, should not lead to noise on X.
Okay.
Okay.
Yes, sir.
But clock activity factor is the highest. So shouldn't it be isolated instead of D? I mean.
So anyway, flop है. Flop में तो आपकी clock आएगी ना.
Yes,
Clock is toggling, so flop तो will use that clock anyways.
So like I was not able to get the answer for the Gagandeep's question. I mean, why you were taking that? What he asked.
Okay. Let us look at the other way around. Let us say clock was on the other side. Clock was on the top and D was coming to the, what do you say, inverter kind of a thing directly. What would happen?
So I mean, if it is coming on the top, then the D would be coming here. So if D is, I'm considering that D, okay, but if it's flip flop, I know that it is edge triggered. So, but D, if it coming, so if at the edge of the clock only, my D can be impact my X node.
But if it comes in the middle, if D comes closer to X, then what happens? It can do something even when it is low.
Even when the edge is not triggered, then also it can impact the X node. Okay. Yes, sir.
We don't want that.
Yes, sir. Okay.
So we are giving this edge sensitivity much precise towards the clock, right, sir? So that as
friends, let's not do these hypothetical experiments. You just draw the circuit and check the functionality, na?
Yes, sir.
है ना?
Yes.
Gagandeep?
Sir, even if I push this clock transistor above the D PMOS, even then the VDD will not be connected to the X, even if the D is making some spurious movements. So it does not really affect the output node in the either case, right? Because that path has to be on.
Yes, that path has to be on. But again, I would say you just experiment, make the circuit with the clock on the top and D in the center, and you will see what happens. I want you to do this
Yes, sir.
exercise yourself.
Yes, sir. I'll try. Yes, sir.
Sir, I just wanted to say one thing, sir. So if my clock is at the top and my D is at the bottom, so there might be a parasitic capacitance between my D and the clock, right? So in that position, when there is a glitch on my D, then there is a possibility that my output might get discharged.
Yeah. So glitches, etc., all those things, dynamic gates के साथ हमेशा problem है ही है, Vaishnav. You will see that problem would exist even here now.
Yes, sir. Yeah.
है ना?
Okay.
Let's see. ठीक है? So anyways, I'm not going to spend too much time on TSPC because I just wanted to introduce